In Type 3 of Lecture 8, we will answer the question, what is an attribute grammar? Abstract syntax trees have one enormous advantage over other intermediate representations. They can be decorated or annotated, so that each node on the abstract syntax tree can have its attributes saved within the various nodes of the abstract syntax tree. This can simplify the task of type checking as the parsing process continues. We will see shortly that an abstract grammar can be a very useful tool in doing the work of semantic analysis. This begs the question, what is an attribute grammar? An attribute grammar is an extension to a context-free grammar that we will use to describe the features of a programming language that either cannot be described in Backus-Naur form or can only be described in BNF with great difficulty. For example, describing the rule that real variables can be assigned integer values, but integer variables cannot be assigned real values is difficult to describe completely in BNF. Robert Sebesta, in his Programming Languages textbook, says that the rule requiring that all variables must be declared before being used is just impossible to describe in BNF. The static semantics of a programming language is indirectly related to the meaning of programs during execution. Its name comes from the fact that these specifications can be checked at compile time, will be checked at compile time, and will be true each time we execute the program. Dynamic semantics refers to the meaning of expressions, statements, and other program units. Unlike static semantics, these cannot be checked at compile time and can only be checked at runtime. An attribute is a property whose value is assigned to a grammatic symbol. Attribute computation functions, or semantic functions, are associated with the productions of a grammar and are used to compute the values of an attribute. Predicate functions state some of the syntax and static semantic rules of the grammar. There are a variety of different types of attributes. The most common types of attributes are the ones that we see here. Type, associating the data object with an allowable set of values. Location, which may be changed by whatever memory management routine the operating system uses. A value, usually assigned as the result of an assignment statement. Name, which can be changed as a result of subprogram calls and returns. And components. Data objects may be composed of several different data objects. This binding may be represented by a pointer and subsequently changed. An attribute grammar is defined as a grammar with the following added features. Each symbol x has a set of attributes, a of x. A of x can be extrinsic attributes, which are obtained from outside the grammar, most commonly from the symbol table. Synthesized attributes, which are passed up the parse tree. And inherited attributes, which are passed down the parse tree. Each production of the grammar has a set of semantic functions and a set of predicate functions, which may be an empty set. Here we see an example of synthesized attributes. You'll notice that this is the abstract syntax tree for an assignment statement. We can see here we have the extrinsic properties that z is a variable which is real, x is a variable that's real, and the constant 2 is an integer. Based on the fact that we have a real and an integer, the only way to accommodate both is for the product to be real. We now have a situation where the assignment now will be handling something that is real because the variable to which it's assigning a value is real. In these two cases, these attributes are both synthesized. Here we see an example of inherited attributes. The token real is at the root of the abstract syntax tree, and its data type is real. As a result, all three of the children on this AST fragment inherit the type real from the root of the tree. We can now rewrite our grammar, and we will assume, for the sake of simplicity, that variables are typed implicitly as in Fortran, where variables with names beginning with I, J, K, L, M, and N are assumed to be integer. Variables beginning with any of the other letters would be real. We have here the start symbol derives identifier, assignment operator, expression. We give this the rule if ID required type is integer and the type of E is real, then there is an error and we'll deal with it accordingly. We next see E derives TE prime. Associated with this is the rule that if the type of T is the same as the type of E prime, then the type of E will be the same as T. Otherwise, the type of E will be specifically real. E sub 1 prime derives plus T E sub 2 prime. In this case, if E sub 2 prime has the same type as T, then that type becomes a type for E1 prime. Otherwise, E1 prime will need to be real. We have the production T derives FT prime, and we use here the rule that if the type of F is the same as the type of T prime, then T's type will be the same as F's type. Otherwise, T will have the type real. T sub 1 prime derives times F T sub 2 prime. And again here too, if the type of F is the same as T2 prime, then T1 prime will have F's type. Otherwise, it'll be real. You notice here that we have the three remaining productions. In F derives ID, F's type will be the same as the type of the ID. F derives constant, F's type will be the same as the constant's type. And the last one, F derives open parenthesis E close parenthesis. F's type will be the same as E's type. In many cases, semantic actions will be handwritten, and we can incorporate them into the existing actions. The rule that says if the ID's required type is the expression's type, then the ID's type will be the same as the expression. Otherwise, it's a type checking error. This can be incorporated into the procedure build assignment. Regarding the rule, if T's type is the same as E prime's type, then the expression's type will be the same as the term's type. Otherwise, it'll be real. This can be incorporated into a new procedure called set expression type, which is placed at the end of the production E derives TE prime. We can place the other rules in action procedures placed at the end of their respective productions. We're going to take another look through creating the abstract syntax tree we did before for the statement z is set equal to 2 times x plus y. When we get to the action push identifier, you'll notice here that we indicate that the type that is required for it is real. As we push the assignment operator on, having the identifier as its left child, there are no additional notations that need to be made at this time. When we go to push the constant onto the semantic stack, we add to it the declaration that its type is integer. When we push the identifier on the semantic stack, we're going to add to it that its type is real. We now build a term where we have the product of a constant and identifier. The constant is integer, the identifier is real, and when we get to show it, we will show that the product must be real. We now push the plus sign operator on the stack with the product that we just finished putting together as its left son. When we get to the point later of assigning a type to that sum, we'll see that it will be real, as the identifier in this case is real and the product is real. We now push the other identifier on the stack. Its type is marked as real. We now build the expression. We have the sum as the root of the abstract syntax tree. Given that the product is real, given that the identifier is real, we now know that the sum will be real as well. We now can build the entire assignment statement. What is clear is that the sum is real. The type required so we can assign it to Z is also real. So everything here will work as it is supposed to.